we are initiating a basin, a very big basin with variety of lithofacies that should explain the continent to marine transition, marine going towards the deep marine and continent towards the terrestrial continental rocks. So what happens? The opening up of the or rifting is not always symmetric, it is asymmetric. So that a larger part of the basin may be at one end, the other end may be very simple. So what has happened in this diagram? This is not Wilson's diagram, this is a general diagram I am taking. This is the early part of the rift. The rift was well developed and the early part of the rift, which is stage B, was kept aside, one side. It is not going to exactly bifurcate, but there will be asymmetry. So this is the old rift volcanoes of the stage B. These are the continental terraces of the stage B. This is the stage sedimentation of the stage B. But now this is new sedimentation of the stage C. This is new sedimentation of the stage C, where you are getting progradational changes in lithofacies from the shallow marine to deeper and deeper part, deep marine. But this facies is also systematically developed. Why I am stressing this now? As in the last stage, if you are going to field and you are finding that felsic rocks are along associated with the mafic rocks, then you may think that this is the bimodal distribution. Felsic rocks are associated with the batholiths are associated with the mafic rocks associated with the rhyolitic volcanism. You can say, yeah, this is the stage B condition. Now in stage C condition, you are getting an association of the older stratigraphy, basin sedimentation, with an unconformity, the upper stratigraphic formations, which may be dominated by limestone and shale. This limestone and shale facies is indicating transgressive facies, increasing more and more increase in sea level, or deeper and deeper association of the facies, deep marine, shallow marine to deep marine, shallow marine to deep marine. Then probably you are in the stage C. You can explain this as the stage C. You also get a ophiolitic soot in stage C, very characteristic in stage C. What is that ophiolitic soot? You may learn in your igneous petrology, but let us see the ophiolitic soot. What does it mean? Ophiolitic soot is a sequence of rock, layered igneous rocks, where in the lower part or deeper part of the mantle, deeper part of the crust or lithosphere, deeper part of the lithosphere, you get the crust mantle boundary represented by moho. Very important. You can get crust mantle boundary exposed on the surface for the older formations, defined as moho. How it will be defined? By the rock association. Dunite peridotite fractionation residue, producing the dunite and peridotite kind of rocks in the lower position, followed by layered gabbro, followed by basaltic sheeted dikes. These are sheeted dikes. What happens at the magma chamber? These rocks are crystallized. At some higher level of magma chamber, layered gabbros are crystallized. They are in the form of layers. At the upper part of the crust, where crust is very brittle, there is neck developed by the magma. This neck we are calling mid-oceanic ridge. So the magma emplacement here is in the form of dikes. Also at the surface, but also in the form of dikes. Two kinds of magma emplacement is there in the form of dikes, closely spaced dikes. Then this ridge is going drifting away. Also at the surface, the magma will be flowing at the surface, and because the surface is below the ocean, below the sea level, you are getting pillow lava basalt. And as you go away, you are also getting sediments. Sedimentation is there. So this kind of distribution is there. This kind of soot is called ophiolitic soot. Then you will say that normally the ocean floor is going to subduct. You are not going to preserve much of the ocean floor for the geological time. But you can get ophiolitic soots, remnants of the ophiolitic soots in the geological conditions because of some geological conditions. One example is the abduction, or some more conditions may be there where the ophiolitic soots can be observed for the older formations. And for the present day condition, you can always see along the mid-oceanic ridges or taking cross section of a ocean floor. These are the pillow lavas. This is one example of the ophiolitic soot exposed. Probably this is from Canada. This is from Newfoundland, Gabbro and Peridotite Association. So they mark more peridotite and anorthosite, some different composition. You can mark more. Stage C is also characterized by transgression. Sedimentation in stage C is characterized by transgression. Very effective and continuing transgression. Very little regression, but mostly transgression. Where you get the distribution of the phases. How you are getting the distribution of the phases? Suppose at this stage you are getting sandstone, beach kind of sediments. After 2-3 million years, the ocean is going to become deeper. So this sandstone will be overlapped or capped by probably limestone. Again, deeper and deeper ocean, this limestone will be capped by shale or mudstone, dark color mudstone. So like that, you get a sequence in stratigraphy, a transgressive sequence in the stratigraphy. So he explains a hotspot may form. It will be active for a while and then it will just die. See, he is considering all the situation. That stage C may not be complete. And he explains the event that sometimes a string of hotspots join together to create convection cell. So mid-oceanic ridge is a linear feature. So a single hotspot cannot explain a mid-oceanic ridge. So he says that a string joining of several hotspots will create a large systematic convection cell. This convection cell will be very stable It turns the hotspot into a rifting system poised to create a new ocean basin, producing also the ophiolitic soot. The process of ocean basin formation begins with a great surge of mafic volcanic activity along one side of the axial rift. The stage B rift is being disturbed. In fact, that is a hindrance for this new kind of magmatism, new kind of stable magmatism joining 1, 2, or 3 hotspots, producing a linear kind of situation, axial situation. So axial rifts do not usually split into two down the middle, but separate along one side or the other. I have explained. At first, the magma is injected as a large number of basaltic dikes into the now thinned and stretched granitic continental crust. The earlier crust was granitic, that is being multiply intruded by the basaltic dikes. That so many dikes form, in fact, that it is finally hard to decide looking at them whether it is original rock granite or it is invaded by basalt, or basalt invaded by granite. This mixture of continental granite injected basalt is called transitional crust. Very important. Granitic and basaltic mingling because of this process is called transitional crust. It is transitional also because you are transforming continental crust into oceanic crust. This initial stage is transitional. So principally because the speed of seismic waves traveling through it is transitional between slower granite and faster basalt. All these deeper structures you can explore by seismic survey. So in the seismic survey, the seismic profiles, the P wave velocity for granite is different, for basalt is different, for sandstone is different. So the P wave record a velocity which is intermediate between granite and basalt. That is also meaning for them to call transition crust. Then the mafic volcanic activity is concentrated at the rifting site, but is not confined there. Feeder dikes cut through the crust at many places, sometimes hundreds of miles to the sides of the axial rifts. This magma may emplace as sill or laccolith, or may surge to the surface to form fissure volcanoes and lava flows. As the volcanic activity continues, the two pieces of original continent begin to drift apart, and the gap between them fills with the mafic igneous rocks. And surge after surge of magma rises from the convection cells in the mantle into the continuously spreading gap as the continents move further and further apart. Within a few million years, the two continents can be separated by thousands of kilometers. So that is all formation of the mid-oceanic region. What happens when this initial stage 3, 4, 5 hotspots or mantle plumes they meet to form convection cell? The convection cell becomes very stable and it continues for millions of years. And a fully developed an ocean is developed. It continues for at least 100 million years. And the ocean is developed. Now let us see the next stage. So by the end of C or the beginning of D, the full divergent margin is created. The other side of the ocean floor, which is connected with the continent. Also in the earlier stage, I called passive margin. That subsides because of the sedimentation and also because of the presence of these older graben faults within the continent. So there is a subsidence, basin subsidence, that also deforms or that also overburdens the ocean floor, causing it a bending. And the sedimentation can be very thick, 5, 10, 14 kilometers, because the sedimentation is continued from stage B, stage C to D. Stage B also is there. Stage B, C and D. So a very thick sedimentary basin can be developed having very thick sedimentation. And again, this is same diagram earlier I have shown. This is the stage B part of the rift. Stage B sedimentation, stage C sedimentation, stage D sedimentation. So it becomes a very thick sedimentation and is the characteristic for the passive margin. The continental margins can be active or passive. So the characteristic for the passive margin are the thick sedimentation. Where do you get such thick sedimentation in India? In Himalaya, in Spiti Basin, in Kashmir Basin, Spiti Basin, Lahore, all these areas, you get thick sedimentation. And probably this kind of association, we need to explore the stratigraphy. Stratigraphy doesn't mean simply paleontology. Stratigraphy means sedimentology also. But at large, it is sedimentary sequence only, sedimentology. So you have to observe this under the stratigraphy. And this is a general distribution of the progradation of the facies from sandstone, shale to limestone. So he writes, heat rising to the surface from the convection cell remain concentrated at the rifting site in the center of the new ocean basin. So as the ocean basin widens, the newly formed continental margin, now called divergent continental margin, we can abbreviate DCM, or a passive continental margin because it is geological passive, moves away from the heat source and cools. Cool crust is denser than warm crust, and as the DCM cools, it sinks. See, the oceanic crust also, the heat gradient in the oceanic crust, you just mind it. It remains there for more than 1 million years. If you go near the mid-oceanic ridges, the temperature of the oceanic crust is higher. As you go away and away from the mid-oceanic region, still the temperature is higher than normal, but it starts cooling. It may take millions of years. So when this oceanic crust cools, it becomes denser, heavier, and it tries to sink, as well as the thicker sedimentation lying above the ocean floor also tries to depress the ocean floor into deeper part, creating this kind of bend of the ocean floor. Thus, in about 5 to 10 million years, the horse, which once were 3 to 5 kilometers above sea level, sink below the waves. Ultimately, it will take about 110 million years for the DCM to cool completely. So he mentions 100. I said 1 or 2 million years, but For complete cooling, it takes 110 million years, or you can just say 100 million years for the DCM to cool completely and stabilize, at which point it will deposit 14 kilometers. It will be below 14 kilometers below the sea level. Meanwhile, a great wedge of sediment is deposited on the DCM, I just explained, expanding and thickening of this basin. These sediments are derived from the eroding continents in case of plastics. How these sediments? Mainly they are received from the continents as plastic sediments. Apart from the chemical and biological activity of the ocean producing carbonates, limestone. It consists mostly shallow marine deposits, because subsidence and deposition go hand in hand. The basin is subsiding as well as depositing, then again subsiding and depositing. So it is going hand in hand. So the stratigraphy in this area, in this basin, will be characterized by the oldest rift, opening of the rift, followed by stable rift, followed by fully developed continental margin of thick sedimentation, recording the increasing transgressiveness, increasing transgressive phases. Then this turns to stage E, that is volcanic arc mountain building. Here it was stage D. D means A, B, C, D, E. Everything is there. These are all remnants of the stage D or till stage D. So what happens in stage E? Stage E is characterized by volcanic arc mountain building process. If you are going back to stage D, then you have to remove this. And mid-oceanic ridge may be there somewhere. So this is explaining one side of the mid-oceanic ridge or the ocean basin. What is created, newly created in stage E is this. So we will see what is this. Stage E is characterized by creation of the convergent boundary. Volcanic island arc mountain building process. So when oceanic crust subducts, it sets in motion a chain of processes which creates several new structural features and generates a wide range of new kind of rocks. At the site of subduction, this is subduction. At the site of subduction, part of the oceanic crust is dragged down into a trench 1 to 2 kilometers below the normal ocean floor and can be about 5 kilometers. Normal ocean floor is about 5 kilometers deep. The subducting oceanic crust begins its descent cold but heats up as it slides into the mantle. And at about 120 kilometer depth, the rocks begin melting to form magma, causing initially fractional melting. The magma, hot and of low density, rises towards the surface, forms batholiths, breaks onto the ocean floor as lava and builds a volcano which eventually rises high enough to form an island. Now, as I said, batholith, immediately you should emphasize the kind of batholith that was explained in stage B. Felsic and Mafic association of the stage B bimodal. That batholith will be different and this batholith will be different if you examine the association. It will be different by chemistry, also by association. So chemistry comes later because you have to go to lab and then examine. But in field itself, you can say, no, this batholith is related to convergent boundary or stage E, and that batholith is related to stage B. And lava builds a volcano which eventually rises high enough to form an island. Skip this. In fact, I should explain this part only. So I said this is remnant of stage E, A, B, C, D, A, B, C, and D. This created during stage E. Now you will question why he did not subducted ocean floor here, or why he did not produce an ocean floor at any the subduction at any other place. Because what happens by the time this fully developed oceanic crust, ocean basin, this side to my right side, the heat gradient is more, ocean is hotter and buoyant. At this side, ocean is cooler, means ocean crust is cooler. So this part of the ocean floor is denser. This part of the ocean floor is lighter because it is hotter. This part of the ocean floor being passive margin is very nicely welded with the continent. So this is very well welded with the continent, very stable. So at this place, the ocean floor breaks. But there is continuous convergence. Ocean floor is moving towards this end, towards continent. And this ocean floor being stable, heavier, it goes down, subsides. It gets subducted. This ocean floor being relatively lighter, it will be uplifted. And this kind of island arc can be developed. So what is this? Ocean subduction. So ocean floor subducting, which has a different kind of composition, by partial melting, which includes the sediments, will develop a different composition of batholith and volcanism. Volcanism will be characteristic of the island arc volcanism, a kind of andesitic volcanism. But let us see. Yeah. Let us see types of subduction. Here some different kind of subduction, island arc. This can also occur under such situation. I am not saying that, and that's why the Wilson cycle is criticized, that they found that this kind of subduction is also occurring, where this layer is subducting, this layer is abducting. This kind of island arc type one kind of island arc type, and that kind of island arc type is called Cordilleran type. This kind is called Cordilleran type, and just now I explained that is this kind of type. Continent island arc horizon. This is another type. This is normal. This is Cordilleran type. So he says the mantle rock above the subducting plate selectively melts and fractionates. The original rock descending into the subduction zone is the oceanic lithosphere, or earlier we explained the ophiolitic soot. So ocean floor is nothing but an ophiolitic soot is going down with the subduction, that is composed of cold basalt and gabbro of the oceanic crust and peridotites of the upper mantle. All this complete ophiolitic soot is undergoing metamorphism because it is going down with the subducting oceanic crust. So this descending slab also carries a lot of seawater with it. So presence of water reduces the melting point, and the melting starts at about 120 km down the water, and heat leads to the fractional melting of the mantle material just above the subduction slab. I explained the fractional melting. Felsic and mafic fractionation is developed. The felsic fractionation being buoyant, being melted earlier, it goes up producing the batholith below the island arc volcanism. So as heating progresses, only the lower temperature phases, lower in the Bowens reaction in the rock melt to produce magmas of intermediate composition. Not mafic and ultramafic, but intermediate composition. And since these are fluid and hot, they rise up through the crust to eventually emplace and solidify as intermediate rocks, diorites and granodiorites. The second fraction or residue, unmelted residue, has a composition of mafic and ultramafic. And higher in the Bowens reaction series, that goes down. If time and conditions allow, the fractionation process can continue and the intermediate magma fractionates into felsic magma, typically producing plagiogranites, leaving behind a magma more mafic than the original intermediate composition. And from the chamber, the magma reaches to the surface as lava and forms explosive composite volcanoes, which are dominated by andesites. See the composition of andesite in your igneous petrology. So andesites, although it can evolve from mafic to intermediate to felsic as the magma fractionates. There can be evolution of this andesitic magmatism from mafic intermediate to felsic because fractionation process may take some time, but the magma can evolve immediately. So this fractionation brings more and more felsic magma at the end. So this is ocean. This is shown as Cordilleran kind of subduction. Basalt or gabbro, or we can say ophiolitic soot going down. This is complete ophiolitic soot, dunite, peridotite, dunite, gabbro, basalt. That entire soot is going down as subducting oceanic lithosphere. While it is subducting, going deeper, say 100 kilometers. On the other hand, this is producing sediments which are trench sediments. These sediments are received from this side. These sediments are also going along with the subducting plate, subducting lithosphere, and here occurs the fractional melting, producing initially maybe diorite, but mostly plagiogranite and the andesitic volcanism. And the residue magma, ultramafic residue, if it continues to accumulate, this is somewhat intermediate magma. So that also tries to come up by convection, and it may produce another rifting here on the other side of the ocean floor. It may produce another rifting. This may be special case, but this is essential to explain the process in the stage E. This may be common, this may be special, but these conditions are also there at the Indo-Burmese side. This condition is also observed. And the basins, these basins are called fore-arc because they are at the front of the island arc. This basin is called back arc basin. What is the significance of this stage? Is paired metamorphic builds. Paired metamorphism. Because two major kinds of metamorphism are happening. One is Barrovian metamorphism, which is low to high temperature and medium pressure. We will see in the diagram. Formed inside the volcano by heat from the batholiths, accompanied by intense folding. Because the batholiths are invading mafic oceanic crust, these rocks are converted into green schist, chlorite epidote rich facies, amphibolite and granulite facies. In association, not independently. You can get chlorite and all these facies at many places, but they are associated. Green schist, amphibolite and granulite facies, they are associated as belt, metamorphic belt. Also earlier now crystallized intermediate and felsic batholiths may be converted into gneisses and migmatites. So there is a metamorphic zone from low grade to high grade occurring in the form of belt. The second metamorphism is high pressure, low temperature blue schist metamorphism formed in the melange of the trench. I will explain with the diagram, but let us read the Wilson's word. It is high pressure because this is convergent boundary and trench sediments are being rapidly subducted. The low temperature is because cool surface rocks are rapidly subducting. So this association of the Barrovian metamorphism with blue schist metamorphism is called paired metamorphism, and it is occurring in the form of belt. Entire plate is subducting, so it is occurring in the form of belt, a linear belt. So that is called paired metamorphic belt. One more metamorphism is important in this stage. At the depth along the subduction zone, the ultramafic layers of ophiolitic soot undergo eclogite metamorphism, and contact and hydrothermal metamorphism would be common along the volcanic pipes and dikes. So you are getting eclogite. This is a very important stage. You are getting eclogite metamorphism associated with the belt, blue schist, green schist, amphibolite, granulite. This belt associated with the eclogite metamorphism, and also some hydrothermal and other metamorphism are there. So this is one pair where blue schist metamorphism is being developed in this belt, linear belt, because of these sediments being undergone metamorphism at high pressure, low temperature. Another metamorphism is this, because of the emplacement of batholiths, granulitic metamorphism, amphibolitic and green schist metamorphism. This is another zone. This is Barrovian zone. This is blue schist zone. So this is called paired metamorphism or paired metamorphic belt in the stage E. Stage E is characterized by, if you get the sediments will be characterized by this. There will be andesitic volcanism, fore-arc are lithic rich sediments. Back arc also lithic rich sediments. So if you plot these sediments, they will plot here. You get associated diorite, plagiogranite, green schist facies, chlorite, and that kind of facies. Blue schist facies may be remnants of trench. All these things are occurring in the suture zone, Himalaya. You can find this kind of association in the suture zone, Himalaya. Now it is deformed. You are simply getting association. Everything is deformed. You cannot see all these things. You can see the association of those rocks. Their lithologic, stratigraphic, and structural association. You can get in that area, entire in the suture zone belt. These are just diagrams. Explaining rising decompressing morphic parents, ultramorphic fractionation residue. Here also ultramorphic fractionation residue, lead fractional melting. These are all alkaline soot. These are calc alkaline soot. That is also probably fractionating into this calc alkaline soot is also fractionating into alkaline soot and ultramorphic residue. These are some examples. Stage F we will explain. We will go for next lecture because it is also very important stage. Next lecture we will finish this Wilson cycle. Even stage G is also very important. We will see next lecture.
Okay, sir.
Okay, thank you.